Hi everyone, it's Dr. Ricardo. We are going to do the third video for Chapter 14 for Chem 240. We're up to page 11 in the notes. And the next topic that we're going to talk about is the relationship between the amount of material that, either reactant or product, that is left in the vessel over time. So if you have a reactant like A here, and it's going on to products, how can you predict how much A will be left over time if you know the reaction's order? Okay, so we're going to do it for first order and second order, but primarily, mathematically, you're going to be responsible only for first order relationships with respect to time. Okay, you're going to be responsible for all the different kinds of rate laws when it comes to calculating the amount, the initial rate, based on the concentrations, because we know for our reaction, this A to A goes to products. If I've already predetermined through a set of experiments that the rate law is the rate is equal to the rate constant times the concentration of A to the x power, but I've done a set of experiments and I've already determined that it's first order. Okay? So that kind of relationship we have to understand if it's first order or second order, and this is how fast it's going if you know the rate constant at a particular temperature and you know what the concentration of A is at that temperature. But what I want to solve for now is following A with time. So this is not a linear relationship, okay? Even in the case of first order, there's not a simple equation that I can come off in here and predict how much A I will have at any given time. What happens here is I start out with a certain amount of A, okay? And since it's a reactant, I'm going to be using it up. So it's going to drop very fast, but it will start to tail off and slow down because if there's no A around, how can A react with, how can an A hit another A to go on to products, okay? So the concentration of A is going to be important. So anytime I have a graph like this is an exponential graph. So an exponential graph is going to be straightened out by taking the log of the concentration of A versus time. So that's what I'm going to show you, okay? So for first order rate laws, we know, right, that I'm just arbitrarily making my question 2A goes on to products. I could have just as easily said A goes on to products, okay? So we know that the rate is equal to minus the concentration of A with time. That's the way we choose to define rate. We're going to follow the disappearance of A. And here we have A disappearing over time. Well, how can I predict how much A do I have at any given amount of time, knowing the rate constant and the initial concentration? Well, that's the formula I'm going to develop for you. So this part we know. This part we know because I'm telling you it's first order. I did a set of experiments already, and I know that that's a 1. Well, if this is equal to this, and this is equal to this, why don't we set rate equal to rate and get this expression? Well, when I get this expression, I see that I could gather like terms and bring this A to the first power underneath here, okay? And I could get this, the change in A over A, right? All of that stuff, I'm just going to switch this guy right here. The change of A over A is going to be equal to K times T, right? Or I should say delta T, okay? So the next thing that you would do is only for those people who are taking calculus, and this class does not have a calculus requirement, is you would say, okay, well, let me not take a big chunk of delta A and a big chunk of time, like look at it from here to here, but let me take an infinitesimally small little piece, and that would change this to dA over A and K dt. And the calculus folks know that you integrate this, and after integrating it, voila, here's the product, okay? So this is not a calculus-based class. I have the derivation on one of the other pages a little bit later on. It is page 13 in here. You can go over it if you'd like, okay? But this step may help some people because they'll see, oh, I know that dx over x is equal to the ln of a when I integrate it. And dt is just going to become time. All right, so the result of that integration gives me this very useful formula. So let me explain it to you. The natural log of this ratio, the ratio of a at time t with respect to the initial amount of a, is equal to minus the rate constant, which we already have determined previously, times the time. Okay? So if I want to know, this also works for something growing in. Okay? If I want to know how much A do I have at this time right here, this is time is equal to 0. This is A is equal to 0. All I need to know is the initial amount of A. How much did I start with? What time am I talking about? Right? How many minutes, how many seconds am I interested in? Am I interested in this far along? Or am I interested in back here? Or am I interested in up here? If I want to find out what any of these values are, I guess my arrows really shouldn't be going that way. They should be kind of pointing up. Right? Because if this is the time that I'm interested in, this is the amount, the concentration I'm interested in. So I know the initial amount, and I want to find it at any other t, one of these other t's. Okay? I could do it just a few seconds after it starts, and then it would not have changed very much. Which situation would that be? That would be like this. Or I could do it a little further along, or I could do it very late, and it would be approaching 0, would be getting lower and lower and lower. Okay? My curve should probably go down a little bit more, something more like that. Okay? All right, so let's try that out. Now, you guys all have a calculator. We talked about this already, with an ln function. And if you do shift ln, you can get e to the x if you need it. Okay? So there's no reason for us to use the log version of this. We can just use the ln version. Okay? So let's try it out. Here's an example, and I'll do it with the ln version, even if I did it on the next page with the log version. Yeah, I'll do it ln version. Okay? So here's what the question says. It says, if the decomposition of N2O5 is first order with a rate constant of 4.8 times 10 to the minus 4th seconds to the minus 1 at 45 degrees, if the initial concentration of N2O5 is 0.1, what is the concentration after 1,000 seconds? Well, one of the keys is to realize that this is in reciprocal seconds and this is in seconds, so we don't need to convert one into the other. If you get this in minutes and you have the rate constant in 1 over days, you need to get them both into the same unit. So you should change your time into days or hours or whatever it is that they're talking about. Okay, so let me write down all my facts. I know that it's first order, so I know that the rate is equal to minus N2O5 with time, okay, and that's equal to the rate constant K times N2O5 to the first power, because they told me this is a first order reaction in N2O5 and N2O5 is disappearing. Well, since it's first order, I know it follows this relationship. The natural log of the concentration of N2O5 at the time that I'm interested in, which is 1,000 seconds, divided by the initial concentration, that gets the little 0, right? That's the initial one. This is the one we're interested in at time equal to 1,000 is going to be equal to minus K, which they gave me, times T, which they gave me. So I've got this, and this All I need to do is solve for the last piece of it. Okay, so let me go ahead and plug everything in. My time was equal to 1,000 seconds. My K, go back to the last page, was 4.8 times 10 to the minus fourth. 4.8 times 10 to the minus fourth seconds to the minus 1. So those two are going to go right here. They have reciprocal units, so they're going to cancel out. I'm going to get something that's dimensionless on this side. Okay, and what concentration did I have? The initial amount of N2O5 at time equal to 0, I believe was 0.1. So the ln of N2O5 to 0.1 molar. Can't do anything with this yet. Just wait on that. And let me go ahead and plug in is equal to minus 4.8 times 10 to the minus 5 seconds to the minus 1 times 1,000 seconds. Let me get all of this done. That's going to just change this. This is 10 to the third. This is going to make this negative 4.8 times 10 to the minus 2 with no units on it, right? This is 10 to the third, 10 to the minus fifth. I'd be left with 10 to the 2. Okay, well, how am I going to get rid of the ln from this side? I'm ready for that step. N2O5 at time t over 0.1 molar. The way to get rid of the ln, this is equal to that, okay? The way to get rid of the ln is to take the inverse log of both sides, which is e. So the anti-log, the anti-natural log of the log will cancel out. You'll see that in a second. So these are going to cancel out. And whatever I do to the left-hand side, I have to do to the right-hand side. This is the anti-natural log, second function natural log, of minus 4.8 times 10 to the minus 2 with no units on it. Okay? This and this are going to cancel. I'm going to just wind up with this divided by 0.1 is equal to what I get for that. Okay? If you want to, this is also e raised to that number. So how am I going to get to, that's the log, that's e raised to that number, or the anti-log? I got to do shift ln. My e pops up. Got to change the sign to negative. 4.8 exp minus 2. So there's two minuses. The exponent is minus, and the whole thing is minus out in front. Okay, let's see how we do with that. Equals. Okay, I get a small fraction. Let me see if that makes sense. It's only 95%. Let me see if that's what I got. Oh, guys, my thing was not 10 to the minus fifth. It was 10 to the minus fourth back here. I just copied the wrong number down. Sorry about that. This is 10 to the minus fourth. This is 10 to the minus fourth. So just my mistake copying here. So that makes this 10 to the minus 1. I'm going to get a much bigger number. It's 10 to the minus 1. This is 10 to the minus 1. The 10 to the minus 1 is just negative 0.48. So I'll do that. Okay, so I need the anti-log, second function, had that right, second function, ln, e to the negative 0.48, right? 0.48 is 10 to the minus 1, is 4.8 times 10 to the minus 1. Okay, big difference. Okay, I get, it's going to be 61% of the old number, 61% of the initial. Look at the answer, the ratio comes out to this is 6187. I'm going to make this 619. Okay, 3 significant digits is more than enough. This and this canceled out. So the N2O5 at time t over 0.1. And then the last step is just cross multiply N2 0.05 at 1,000 seconds is going to be just 0.1 molar times 0.817. So this could be any unit of concentration because this has no units. So this could have been molarity, molality, parts per million. It actually even could be mass, okay? Whatever unit you have here, that's the unit you'll get here. The most important thing is when you get to this step, even if you left here the initial amount, go back up to here, before you plug this in, right? This stuff over here, after you take the log of it, tells you what fraction you have compared to the original. So we have 0.619 compared to the original. So that's going to make the final answer 0.0619 molar. Okay, I'm going to compare that with my next page in the notes, which I did it originally with the LOG version. So here's me doing it with the LN version, 0.0619. Everybody see? From here to here is very easy. Just multiply both sides by 0.1. They cancel out here, and I get it down there. Okay. And what happened when I did it here? Pretty close. Perfect, exactly, right? Here I got 0.062 is left after 1,000 seconds. Okay. Another way to write this formula is kind of cool, right? The way to write the formula is if you want to know how much material you have after a certain amount of time, in our case, 1,000 seconds, it's going to be equal to the initial amount of material, in our case 0.1, times the antilog of negative kT. So just kT. So this is a nice rearrangement of this original formula. So I would keep both of them handy, right? This one and this one. Let me make it a little bit bigger. We'll talk about when to use which one. Okay, a little autofocus. Right? So here's the original formula. Here's it rearranged, all ready to solve for AT. Okay? So how much stuff, if it's a first order reaction, how much material do you have left after time t? It's equal to the amount that you started with times the antilog of minus kT. Last way that you could write it, all right, for those people who want to do it this way, people who have taken a lot of math, it's A at time t is equal to the original amount, A0, okay, multiplied by e to the minus kt. So how's that? That's the last way that you could think about it. 1, 2, or 3 will get you the correct answer. Okay, this formula is only for first order reactions, when it's first order in just one thing. So the overall order is first order. If it's second order in a particular thing, you have to do something different. Okay, and I will show you that. Okay, page 13 that I was showing you, I'm going to skip. Here's the derivation going from the rate of the reaction, which we were going to measure as the change in A over time, is equal to K times A. So you rearrange and then do the integration. There's your working formula right here. Okay. All right. So I'm going to introduce a concept that works very nicely for first order reactions, and I'm only going to ask it to you about first order reactions. So when it comes to kinetics, honestly, in this chapter, and someone is asking you how much stuff has been created or lost over time, you're only going to be responsible for doing first order reactions. First order reactions have something called a half-life that's independent of the initial concentration of the material. Only first order can say that, okay? Second order, third order are more complicated. The half-life, the amount of stuff you have remaining after, the amount of time it takes to go to half of the original material for any other order does depend on how much you start with, but not for first order. for first order, the equation works out that it's independent of that. So there is a set half-life for a particular material as it either decays or grows in when it's first order. So let's talk about it. So the half-life, okay, for anything has the definition of it's the time it takes for the concentration to decrease to 1/2 its initial value. So that's the definition of the half-life. So you could do this for any order, okay? But it's only going to give you this super simple formula for first order. Okay, so let's take our same system. We have A. A is a reactant. It's going to decay to go to products. And it's for first order reaction. So this is first order in A. Okay? The rate is proportional to the concentration of A. If the A concentration is double, it's going to be decaying twice as fast as it would initially, as it would ordinarily. Okay? If it's 10 times the concentration, it's going to decrease 10 times faster. Okay? So this is a first order relationship, and we're watching A disappear. Right? Good. All right. So here's our first order rate law. When I have my ln over here, I don't need the 2.3, so I'm going to erase it. I erased everywhere else. I just forgot that one. So here's my whiteout. Might as well do it right in front of you guys. Okay. So that guy is good to go. All right. Let's take our formula up here and do a little teeny bit of plugging in. Okay. Little teeny bit of plugging in. And what we're going to get is if T is a special place called T to the 1/2, right? So it is the time it takes to go for the amount of A to go to 1/2 its initial concentration, then at T equal to T to the 1/2, AT is equal to 1/2 A0. So why don't we plug this in for T and 1/2 A0 in for A? Because remember, A is AT. Okay? It's how much stuff you have after a certain amount of time. All right, so that's what I'm going to do. I plug those two things in to this equation here, and I wind up with ln of 1/2 times A0 over A0. Those two A0s cancel out. And here I have negative K, not just to the T, but to this special place T to the 1/2. So you see what I did? I substituted T to the 1/2 in for T, and I substituted 1/2 A0 in for AT. They cancel out. And look what I get. I get the natural log of the number 1/2, just the number 1/2, is equal to minus KT. Well, that's just a number, so let's just take the natural log and see what we get. Well, if you take the natural log of the number 1/2, let's see what you get. So, ln .5, right? You get negative 0.693. So this whole left-hand side works out to negative 0.693. But you have a negative sign over here. Look, all the way throughout all the formula, you had that negative sign. So those two negative signs cancel out, and you get this really cool equation. The rate constant at a certain temperature for a first-order reaction times the half-life is equal to 0.69. This is universal. Now, obviously, you're never going to use this equation to solve for 0.69 because we know the answer is 0.69. You're going to use it this way, right? Rearrange this and solve it for T to the 1/2. If I give you the rate constant for a first-order reaction and I ask you, what's the half-life? All you have to do is take the number 0.69 and divide it by the rate constant, okay? Again, these are at a particular temperature. If I give you the rate, if I give you the half-life of a particular material, that's first order, right? The decay of that material chemically is first order at a certain temperature, and I ask you for K, you just take 0.69 and divide it by T to the 1/2. Pretty powerful. So the relationship between the half-life And the rate constant is independent of the concentration. It's very dependent on temperature, so we're going to keep the temperature constant. So I should put at constant temperature, at constant temperature, right? So the temperature that I'm evaluating K has got to be the same temperature that I'm evaluating T to the 1/2. And you know temperature with a capital T is temperature. Okay, let me show you this quick graphic. And this graphic is very nice. Oh, it fits on the page nicely. Good. It shows you everything, all of the formulas for first order when the overall reaction is first order and when the overall reaction is second order. Okay? I have an asterisk on here because this is the one that I'm going to ask you to evaluate mathematically. Over here, I'm only going to ask you to understand it in theory. Okay? Especially what graph you would have to make in order to see if something is second order. Okay? So again, if I have my chemical reaction, 2A goes on to products, and the rate we've already figured out is first law, rate is equal to K times whatever that chemical is to the first power, then everything here is going to hold. Well, first of all, the graph is going to look like this. It's going to go down with time. Okay? We know that it's first order, it's overall first order, and it's first order in A. We just talked about the relationship between concentration and time is equal to the natural log of the concentration at whatever time you're interested in divided by the initial concentration is all equal to minus K times T, where T is the time. K is the rate constant. We know the half-life relationship. We just derived that. They're reciprocal to one another. One's in the numerator, the other one's in the denominator, and they're related through the ln of 1/2. Okay? What graph would I have to make to straighten out this graph, right? If I just plotted the concentration of A versus time, I get an exponential decay. But if I plot the natural log of A, right, this is A, this point over here is A0, but this is the graph of A versus T. If I graph the natural log of A versus time, okay, I get a beautiful straight line that looks like this. So the natural log, since this is decaying, A is a reactant, it's going to go down like that. If A was a product, it would just go up. Okay? And the slope of this line is equal to the rate constant. Okay? So the graph, you do have to know this, the natural log of A versus T will give you a straight line. Okay, if you have a second order reaction, well, if it's second order, it looks like this, right? So it has nothing to do with this coefficient of 2. We've experimentally determined that it's second order. Let me get a better pen. We've experimentally determined that it's second order. We know that this guy is 2. Okay? The graph still pretty much looks like this. You couldn't necessarily tell it. It would be an exponential decay. It would decay faster, but you couldn't just tell it from the shape. It's certainly not going to be straight. Okay? Well, what is it? What is its relationship? Well, very interestingly enough, the equation that relates the concentration of A that you have remaining at any time is equal to 1 over AT is equal to KT plus 1 over A0. So you have all the same parts, it just uses a different formula. Okay? So you have to do a lot of flipping over and stuff. So what you would do is multiply the K times the T, add on 1 over the initial concentration of A, get that answer. That answer is equal to 1 over AT, then flip it over and you'll have how much A you have left at time T. Okay? Here's the half-life relationship when it's second order. T to the 1/2 is equal to 1 over K times the original concentration of A. So remember I made such a big point about for first order, the first order half-life is independent of the concentration. That's not true of second order. If you start with more stuff, okay, you will have a different half-life than if you start with less stuff. And let's see, since it's in the denominator, if you start with more stuff, you'll have a smaller half-life than you would if you start with less stuff. That kind of makes sense. And last thing, this I will ask you on a test, okay, on a qualitative question. What do I learn if I graph 1 over the concentration at a certain time versus the time? Well, if that turns out to be a straight line, then I know that it's second order in that species. If this one turns out to be a straight line, I know it's first order. Okay? So again, here's what the original graph would look like if it's second order. Here's time. Here's how much stuff you have left. If it's second order, it's going to come down steeply. Here's the original amount of, that's 8 that you started with, right? That would be our A0. It's coming down super steep, okay? Well, if I graph 1 over A T, this will give a straight line. It will come up like this, and the intercept of the straight line will be 1 over A0. Okay? So this guy will give a straight line. Okay? So that's all that I would ask you to do, is which one straightens it out? Taking the reciprocal of A or taking the natural log of A? Take the natural log of A versus T, first order. If the reciprocal of A versus T gives you a straight line, that would be second order. Okay? So this is a good sheet to have ready, have around. And again, the top line is by far the more important one for you guys. This is a little beyond the scope of the class. Okay, one more topic we're going to talk about is the relationship between the rate constant and temperature. Okay, so we're going to wind up with a formula called the Arrhenius equation, and the Arrhenius equation is a mirror image as the Clausius-Clapeyron equation. So it's going to be able to predict the change of the rate constant with time, just like the Clausius-Clapeyron predicted the vapor pressure as a function of temperature. I said time, I should have said temperature. So the Arrhenius equation that we're going to derive here is going to give us the effect of temperature on the rate constant, because rate constant is very much a function of temperature. So here's rate constant K. So let's read through this and come up with the equation. But you already know how to work with this kind of equation from Clausius-Clapeyron. Okay, in order for a reaction to occur, reactant molecules must collide with an energy greater than some minimum value and with the proper orientation. Okay, so if A is going to react with B, okay, and I need to form a bond here, right? Not only does A have to react with B, it's got to hit with a certain amount of force, but it can't hit like this. How's my finger going to go in there, right? How's my thumb going to fit into that pocket if it hits the wrong side of my hand? So all of these are wasted collision, wasted collision, wasted collision, wasted collision, wasted collision, wasted collision, woof. So orientation does matter, right? Because molecules are not alive, they can't swim towards the hole, they're just hitting randomly. So here's the factors that are going to affect it. So the most important thing is called the energy of activation. Energy of activation is capital EA. And the energy of activation is the minimum energy for collision for the two molecules to react. So the minimum energy of collision required for the two molecules to react. Energy of activation is going to always be a positive number. It always is an endothermic process. They require energy in order to hit. So the energy of activation is going to be a positive number. Okay? If you've seen energy diagrams already, the energy of activation is the hill that you have to go over in order for the molecules to react. Okay, so actually, let me finish with this, and then we'll end with that little review, because that I think you already know. Okay, so that's the case, all right? So we have the energy of activation is always positive, and we know that the rate constant is equal to these three factors. The first factor is called Z. So Z is the collision frequency. So Z is how many times the molecules hit one another. P is the fraction of those collisions that occur with the reactant molecules properly oriented. So in my little example here, maybe 1 out of 10, P would be 0.1, because only 1/10 of the collisions occur fruitfully, where the two particles get together in a way that create a bond. Okay, all the other hits are wasted except for the correct one. Okay, so this is just a fraction, and this is a fraction. Okay, so we're going to take P and Z and combine them. Okay, so what is F? Well, F is going to be related to the energetics of it. So this is orientation. This is how many times they hit. This is if they hit hard enough. So if they hit hard enough is called the fraction of collisions that have an energy of that have a kinetic energy greater than the energy of activation. So you have to have enough velocity. Kinetic energy is directly related to velocity, right? You have to have enough velocity, enough kinetic energy, so that when you hit, you go on to making breaking the old bonds and forming the new bonds. So F turns out to be equal to E to the minus energy of activation over RT. So this little piece right here is going to fit in for F. So plug that in for F, and we see that we're going to call Z and P, put them together, because these things are something that would be very difficult to measure independently, and Z and P together, how often they collide, and if their collisions are oriented correctly, multiplied together are going to give you one factor. So we're going to take two things that are very hard to measure, and we're going to group them together. That's called the Arrhenius frequency factor. Okay? It combines how often they hit times are they hitting with the correct orientation. So let's say they hit 4,000 times a second, okay? But only half of those collisions, because this guy is 0.5, are headed in the right orientation. So we'd have 4,000 times per second multiplied by 0.5 to give you 2,000 for the A factor. So it combines orientation and frequency of hitting. Because again, if you don't hit, you can't react. All right, last thing. Not all of those collisions, even though they're oriented correctly, and even though they're hitting a lot, right? They're hitting 4,000 times a second. Half the time they're oriented correctly. We're down to 2,000. We need to cut it back a little more. Why? Because only a fraction of them have enough energy. You have to have enough energy, be in the right orientation, and you have to hit. So that's the F part. So what happens is when EA gets bigger and bigger, when temperature gets high enough to overcome E over A, this factor will become very small, and this number will approach 1. And then you'll get to the point where 100% of the collisions, if the temperature is so hot, 100% of the collisions will have enough energy to go on to product. Then you take that fact that F is equal to 1, but you still have to multiply it by P and Z. So we had, remember, 4,000 collisions. Half of them are fruitful. Now we're at such a high temperature that all of them have enough energy. This guy in the middle would be 1. So we'd have 2,000 for our K. Does that make sense? So orientation, how often they hit, and if they hit with enough energy, So this and this we're going to combine to A, and F we're going to gather up as this whole term here, right? Temperature gets higher, it's going to make this factor go to 1, right? E to the negative, as this guy approaches 0, any number to the 0 power is 1. Okay? All right, let me just write this down for you here, and then we'll move on to the next page. Let's see what the next page looks like. Okay, I did it over here, so this is good enough. All right, so this is called the Arrhenius equation. We're going to derive it. It's the mathematical equation which expresses the dependence of the rate constant on, this is not time, this should be temperature. Okay, that's a big mistake, right? Time we already did. So this is Arrhenius equation, mathematical expression, which expresses the dependence of the rate constant on temperature and Kelvin temperature. Okay, all right, so K is equal to Z, P, F. I put the Z and the P together, that's equal to A. So now I have K is equal to A times F, but we said F was equal to E to the minus the energy of activation over RT. And that's the exponential version of the Arrhenius factor, the Arrhenius equation. Okay, here we go. If you want to know the rate constant is equal to the Arrhenius frequency factor multiplied by E raised to the minus energy of activation over RT. Okay, what R do we use? Okay, and what T do we use? Well, the R we use is the same as the Clausius-Clapeyron equation. It's the energy R, 8.31 joules per mole Kelvin. Make sure your energy of activation is also in joules per mole. Okay? If that's the case, everything will cancel out and you will get a unitless number here that you'll be raising it to. So this whole part is just going to give you the fraction that have enough energy. K is, if temperature is very, very high, this whole term will approach 1. Good. Okay, let's take the log form of that. Anytime you have a K, you can take the natural log of both sides. So I took the natural log of this side and the natural log of that side. One of the functions of logs is you can break up the log of a whole thing is the log of the first thing plus the log of the second thing. But this guy has a minus sign on it, and you take the log of E, those two things cancel out, so that's how you get minus EA over RT. So I could do that a teeny bit slower for you. It would be ln of K, right? ln of K is equal to ln of A, right? And then I have ln of E, right? Go back up here. ln of E raised to the minus EA over RT. But the ln of E, the natural log of E, cancels out. And now this minus sign is the first thing standing over RT. So I get ln of A minus EA over RT. Okay, well look at this. This now can be rearranged into something that we could graph and get a 2-point formula for it. So that's what I'll show you over here. Right? So you could graph the natural log of K versus 1 over temperature, and you will get a straight line just like the Clausius-Clapeyron equation. If you take the natural log of the rate constant versus 1 over temperature, you will get a line that goes down like that, and this intercept here has some meaning. This intercept, right? This whole thing, you could rewrite this as minus EA over R times 1 over T, right? So this is the slope. The slope of this line would be minus EA over R, and the intercept would be ln of A. So this is how you can dig out the Arrhenius frequency factor by doing a macroscopic experiment. Okay? All right. Now, last thing, right? This is, first of all, interesting. This doesn't matter what kind of rate constant it is. It doesn't have to be first order. It could be first order, second order, third order. Look how much this is looking just like the Clausius-Clapeyron equation. Okay? The Clausius-Clapeyron equation, this was ln of vapor pressure versus 1 over T. Okay? Well, you can make a 2-point formula just like you did that. If you have 2 points, 2 points define a line. So if you know this temperature and the K at that spot and the temperature and K at that spot, you can plug it in to an equation that looks like this. Okay, so here I did it with here's the ln version, here's an log version, but we know y is equal to mx plus b. So here in my log version, that's the old b. Here in the log version, this got a 2.3 in the denominator, but I could have done exactly the same thing over here. This would be y, this would be b, and this would be EA over R is the slope times 1 over T. Okay, so a plot of the LOG or the the LOG of K or the ln of K versus the Kelvin temperature will give a straight line with a slope equal to minus EA over R and an intercept of ln of A0. Right? Any order. This is the relationship of the rate constant with temperature. Okay, here's the working formula then. The working formula is identical to Clausius-Clapeyron. Look at that. Once I do all the algebra, okay, once I do all the algebra, remember this is a downward sloping line. I'll show you on here. It's a downward sloping line, right? So really, EA over R has a negative sign on it. So what I do is I pull that negative sign, or I multiply that negative sign through here, and it changes 1 over K2, 1 over T2 minus 1 over T1. It changes the order just like it did in Clausius-Clapeyron. So that part is just algebra. So the working version for us, and we can practice one, okay? The working version for us is the natural log of the ratio of two rate constants, okay? One at a higher temperature compared to the other one at a lower temperature, okay? Or one at the initial temperature and one at the final temperature, doesn't matter, okay? Just be careful to associate this K is with this temperature, this K is with this temperature. Honestly, in 100% of the cases, the K is going to be larger with the larger temperature. So the 2's are going to be the higher ones. The 1's are going to be the lower one. Okay? All right. And you don't have to worry about a 2.3. It's just EA over R. So what's cool about this, first of all, make sure you put the temperatures in Kelvin. Okay, what's cool about this is if you know the rate constant at two different temperatures, you can use it to calculate the energy of activation. So let's go ahead and do that, okay? I'm gonna try to come up with one, okay? So here's the one I'm gonna come up with, and that's where we're gonna end this video. So how about this? How about I do two experiments, okay? So experiment number one, again, I run the chemical equation, I run the chemical reaction, and I'm able to measure the rate and ultimately measure the rate constant. So I find out that at this first temperature, at T1, which will make 100 Kelvin, okay? So it's a cryogenic temperature. It's lower than absolute zero. T1, I measure K, and the rate constant comes out to be 0.15 molarity per second. We'll make it first order, okay? This is T1, okay? That's experiment one. Then I do the experiment again at a higher temperature. And I measure the rate, and then if I know the rate, I can calculate the rate constant because I know the rate law. At this higher temperature, let's make it 300 Kelvin, right, which is just a little bit warmer than room temperature. It's going to go much faster, okay? So I raise the temperature. Its new Kelvin is going to be, I'm going to make it 61.2, so it changed dramatically, molarity per second. Okay. So it went up 200 degrees Kelvin, and the rate constant increases. Higher temperature will always give you a higher rate constant because the molecules are going to hit each other more often. That's good, right? It's going to raise the Arrhenius frequency factor, but more important, at 300 Kelvin, a larger fraction of them are going to have enough kinetic energy to break the old bonds and form the new bonds to overcome the energy of activation. So the kinetic energy is going to be higher. They're moving faster. They're going to have enough energy to overcome, they have more energy than the energy of activation. All right, so let's plug in. So what am I going to solve for? I want to know EA. What is the energy of activation? All right, so Ln, right? The 2's are going to be the higher numbers. That's good because if the 2's are the higher numbers, I'm going to get all positive numbers. So this divided by 0.15, they have to have the same units. Okay? Nobody's saying what the units are, but they have to have the same units. If you're solving for one of these and you have the other one, yours will come out with the same units as the other one. Okay? Is equal to EA over R times, this is the weird part, this formula, it's got T1 first, 1 over 100 Kelvin minus 1 over 300 Kelvin. 1 over 300 is a smaller number, so this is going to be positive 2. Okay. Let me do the left-hand side and the inside. Oh, I know R. R is 8.31 joules per mole Kelvin. So I can put that in too. All right, so I'll do this part, the left-hand side. Ln, okay, parentheses, 61.2 divided by 0.15, close the parentheses. Hopefully I didn't accidentally hit something. I get this whole thing comes out to 6.01. Okay, I did that whole thing in one step. Okay, you could see back here, ln 61.2 divided by 0.1. Let me see if I could scroll along. And then I just closed the parentheses. Okay, so that's all in there. All right, that's the nice thing about using parentheses on your calculator. You don't have to write a lot of stuff down. Okay, here I have EA, which I'm going to solve for, over 8.31 joules per mole Kelvin times, let me get this whole part. I can do that in parentheses too. So open the parentheses, 1 divided by 100, close the parentheses, minus, open the parentheses, 1 divided by 300. Okay? You can do it all separately if you want, but that's kind of nice. Okay, I get everything over here inside these brackets comes out to 6.67 times 10 to the minus 3. Okay? All right, last step. I want EA by itself, right? So I am going to bring this guy up here. This guy's coming underneath, right? I'll leave the EA over here so you don't get confused. I have 6.01. This guy is going to get multiplied when I cross multiply, 8.31 joules per mole Kelvin. And under here, this was in the numerator, so it's going to be in the denominator, 6.67 times 10 to the minus 3. Okay, what unit did this have? This had units of 1 over Kelvin. Okay? This also has units of 1 over Kelvin. Kelvin in the denominator, Kelvin in the denominator. So that cancels out. So my answer, when I'm done, is going to be in joules per mole, which is an energy unit. That's perfect. So how much energy does it take per mole to overcome this energy of activation? Do I have enough? Okay. So 6.01 times 6.31, oh, sorry, 8.31. 6.01 times 8.31, all divided by 6.67 e to the negative 3 equals. Okay, wow, I just guessed that one and it comes out reasonable. 7,487 joules per mole. Okay. How many kilojoules per mole is that? That's 7.487 is 49 kilojoules per mole. So a little bit low. Most chemical reactions would be a little higher than that. But I didn't guess badly. I got a reasonable number. Energy of activation will always come out positive. So you're going to be able to use this formula. We used it to solve for the energy of activation. But you could use it if I give you the rate constant at a certain temperature and ask you what is the rate constant at another temperature. You put in and give you the energy of activation. You put in the energy of activation. You put in K1, T1, T2, and you'd be solving for K2. So using the Arrhenius equation, just like the Clausius-Clapeyron equation, most of the time people are asking you either for K2 or the energy of activation. And this was Clausius-Clapeyron. The only difference was this was delta H of vaporization instead of energy of activation, and these were vapor pressures, right? P2 and P1. Everything else is the same. The math is the same. The concept, in a sense, is the same. Okay, I'm going to just draw one more picture for you, and we'll leave you there, and we'll pick up the next video with reaction mechanism. So we'll definitely get done after the next video. Okay, so first thing, this is a review from Chem 1, so you'll like that. If here's a chemical reaction, let's make it an exothermic chemical reaction, so it's going to give off heat. Starting out with this amount of energy, I'm going to end up with this amount of energy. This is time over here, right? Some people call it the reaction coordinate, right? As the reaction goes on, right? This is before the molecules hit, this is during, and this is after. Exothermic, we start over here and we go downhill. So I'm going to have A go to B. Okay. All right, so this is A and this is B. All right. Delta H, this is enthalpy, right? This is H over here, which we call enthalpy. It's the heat of the reaction at constant pressure. Okay, so the enthalpy of the reaction is downhill. So the change in H, delta H, went downhill, is going to be negative some number. So I'm going to make each one of these equal to 100. So let's make it negative 200. So this is the delta H, the difference between the starting point and the final point. You knew that. Delta H is equal to negative 200 joules. Okay, but here's our new guy. What did we just talk about? I have to get up over some barrier, right? If I can't get up over this barrier, they could be hitting all day and they're not going to go on to create B. So I need A's to hit into other A's, rearrange, and A transforms into B. Okay? This is the energy of activation. It's the energy in the energy level diagram. It's the energy between the starting place and the highest place. It's always positive. It's the energy of activation. In our example that we just did, we got this number to be something like 7, but I'm going to make it a little bigger here. Let's make this about 60. Positive 60 I need to go over. I need to go up, over it, and down. Okay? All right. Let's take a look at our distribution diagram that would go along with this. So the distribution diagram was, this is temperature, right? This was time over here. So anytime it's capital T, it's temperature. And you can make it in Kelvin, right? And this is the fraction of the molecules that we're talking about, okay? So this is their energy distribution. So this is the, at a certain temperature, what is the kinetic energy of the molecules? How is it distributed? Okay? All right. So what happens is that at a certain temperature, all right, at a lower temperature, the distribution of the molecules. How many? Actually, let me do this. Let me switch this. This is a mistake. This should be, did they have enough kinetic energy? Okay, and this is at a lower temperature, and this is the molecular distribution. So this is the fraction of molecules with that energy. Okay. All right, so at this low temperature, this fraction has it. So the area under the curve, right? The area under the curve, if I was to take all of this, I would get 100% of the molecules because they have to have some distribution. So it's not just the height, it's the area under the curve. So about half of them have an energy, at this temperature, half of them have a kinetic energy that's lower than this number, half of them have a kinetic energy that's higher, okay? All right, when I raise the temperature, this spreads out. We saw this for the vapor pressure picture too. It spreads out, but it also moves further to the right, okay? This is the higher temperature. Okay. All right, this, let's make a solid line right here. This is the energy of activation. Only molecules that hit each other with this amount of energy or higher, right? This is the kinetic energy of the molecules. How many of them have it? Okay? All right. At a lower temperature, hardly any of them, just this little bit over here, just this tiny little fraction, that area under the curve relative to the rest. Only that small percent have enough energy that hit hard enough so that they can go on to react. When I raise the temperature now, look at this. Everyone over here, everyone on the right-hand side of the curve has enough. And it keeps on going. There's even a few more guys over there. So at the higher temperature, almost half of them, maybe a third, right? This is still smaller than all of that. All of those molecules don't have enough energy. But man, at that higher temperature, 300 Kelvin, like in the question we just did, I exaggerated the number of molecules that hit hard enough to go on to product. See the difference? Lower temperature, hardly anyone. Higher temperature, more. So when you're raising the temperature, you're increasing the kinetic energy of the molecules so that more of them, some of them are going faster than the average, some of them are going slower than the average, but they make a distribution. This is the distribution of the molecules with that kinetic energy. Here's the average amount of kinetic energy. Now, this is not temperature, this should be kinetic energy. This guy has an average that's over here, right? And this is the line in the sand. This is 60 joules. This is the amount of energy that the molecules must have in order to go on and react. And many, many, many of them have it at a higher temperature. So when you raise the temperature in a chemical reaction, why does it go faster? First and foremost, because you increase the percentage of molecules with enough energy. That comes right from the Arrhenius equation. Look at the Arrhenius equation back in this form. You're increasing this factor, not just the percentage which have enough energy to go on and react, right? You're not touching their orientation, and you're also actually increasing how often they hit. They hit a little bit more often, but mostly it's over here. Okay, so somebody asks you, why does temperature affect the rate constant? Because when you raise the temperature, you're increasing dramatically the amount of molecules with enough kinetic energy, the amount of molecules with enough kinetic energy to go on to product. That big chunk over here compared to At the lower temperature, almost no one. Look, everyone is over there. It's like 1% to 99%. 99% don't have a high enough kinetic energy at the low temperature. At the higher temperature, come on, man, that looks like 40% to me. 40% have enough, 60% don't. What would happen if I raised the temperature even more to a third temperature? This was 100K, this is 200K, maybe 300K looks like that. Oh, I'm sorry, I had 300K, so this was 100K, 300, maybe 500 Kelvin, right? Wow, look at that. This graph, the average is here. The average molecule has that much kinetic energy. Everyone, the percentage underneath the curve, let me do it in yellow. Right? Anybody to the right of the line has enough energy to react. So at this higher temperature of 500, oh my goodness, all of these guys, all that area under the curve, all of those have enough energy. It's just this tiny slice that doesn't. So let's estimate the area under the curve in that slice compared to this big one. Man, that looks to me, this looks like 92% to maybe like 8%. So at the highest temperature, almost all the molecules have enough energy, so it will react super, super fast. Okay, that's enough for one day. All right, we only have one more section for chapter 14. We'll see you guys next time. Have a great day.